Okay, talk a little bit about graphing today. I know we started talking about graphing before the break, but it's been about 10 days, so let's get back at this. Now, some of the reasons, and I'm going to get you to jot these down, why we would want to make a graph is that we are visual and we like to be able to look at patterns. And a graph allows us to take numbers that might look at first to be, if not random, not necessarily related, and it allows us to see if they are. And by looking at the pattern that we find on a graph, as a physicist, you're able to figure out what's going on. So graphs, and you can just jot this down on your notes page here, they allow us to see patterns. Now, if you move on in physics, one of the things that you will also learn is that graphs allow us to make predictions. Graphs also allow us to describe new phenomena, which is a fun word to say. Phenomena. There we go. Okay, so we can see patterns, we can make predictions, and we can describe new phenomena. And we'll look at some of those things as we go through this. Okay, so now graphs need to have a title. The title needs to be both descriptive and accurate. So it's going to say whatever is on the y-axis versus whatever is on the x-axis for whatever it's for. So if we're looking at distance and time, it would be distance, which will go on the y-axis, versus time for, and if it's a person running, so it would be distance versus time for a person running. We need to have axis labels with units. So you have to describe, or sorry, I should say write down that the axis on the y is distance, and the units are meters or kilometers. And then the same thing for the x-axis. So it's going to be time, and so your units are hours or seconds or minutes or whatever they happen to be. The scale for both x and y needs to be even. It's not like a bar graph where you just put down whatever you've got for your x-axis. Okay, both x and y need to be even. The points need to then be marked with a circle or a square around them, and we need to have some kind of a line of best fit that we draw in. That's going to be drawn with a ruler. Okay, you can add this. A ruler. This is, of course, assuming it's a straight line. If it's a curved line, if the dots or the points look very much like they are curved, then you would in fact draw a smooth curve that goes as close to all of them as possible. Okay, so if you flip to the back of this first page, okay, we're going to be, you can see there's some grid paper there. I'm going to give you some data here. You can pause it when you've got it on the screen, and we're going to quickly graph that data. Okay, and so we're going to have both distance in meters and time in seconds. Okay, and 0 and zero, distance of 1.5, time of 3, 2. Okay, so there's our data points, not exceptionally difficult. Now what we want to do is we want to make the graph reasonably large so that we can actually see what's going on. I am capable, if I scroll down to, well, I'm scrolling down, you'll have to flip to the next page. I'm capable probably of making the entire graph down in this corner, but there's no point. You're given a large sheet of paper, let's make it a reasonable size. So first thing to do is figure out where your axes are going to go. Let's put it somewhere here. You don't have to copy mine exactly. We want some nice straight, fairly large lines. Eventually, lovely. Okay, draw another line here for my x-axis. Okay, lovely. Now, if we look on at our data, which I will leave on here in just a second, we have distance. This is going to always go on the y. In graphs, time just about always goes on the x-axis, and distance or something else will always go just about always on the y-axis. So our y-axis has to go at least from 0 up to 5.5. Well, given what I've got here, let's start down here at 0. Call this 1, 2, 3, 4, 5. Now this would be 5.5 here. We'll go right up to 6 because I've got the room. Okay. And our time has to go at least up to 7 seconds. We can go a bit further if we need to. Again, 0 will be right here. Let's go 1. Notice I include 1 even though it's not up there. 2, 3, 4. It's an even space all the way along. 5. Oops. Oh, that's worst 6 in the world. 6, 7. There it is. I guess this would be... Oh, don't grab onto that. 8. I'm missing a couple things at this point. I don't have a title yet, so let's add a title to this. It's going to be distance versus time for an object in motion. Okay. I need to know what the scale is on this side, what the units are here, as well as what I'm talking about. And on this side, we've got distance in meters. So I need to say both of those things. So I've got, okay, distance in meters. On the bottom, I'm going to have time in seconds. At this point, I want you to pause, graph the data, and then check it. So pause, do it now, graph the data, and check this. Alright, so here's the data that I graphed. Now, as you'll notice, these points do not make a perfectly straight line. And so what you do with them is going to be a little bit dependent on exactly where you put your line of best fit. That all being said, the data does, if you look at it with your eye, look sort of close to being a straight line. And so what I did here with a line of best fit, I've got the line going through the point at 0 and 0. Because that one we can figure, we know pretty accurately that it's not moving at the beginning, or it's at whatever starting point at the beginning. Most likely what would have happened to collect this data is that we would have had some problem with data collection. Maybe our timer was off a little bit, maybe something with the distance measurement was off, and so we didn't get a perfect graph. But it's close to straight, so we're going to use it. We're going to do a few things with it. If I was marking this, just so you know, the marks would go, did you plot the points correctly? In this case, yes, they're plotted correctly. Do you have your axes labeled? Yes. Distance there, meters, time there, seconds, lovely. Is there a title? Yes, there it is. What about the scale? Scale's good here, scale's good here. And what about the line? Now, it's a line of best fit. There's actually very complicated mathematical ways to draw a line of best fit. In this case, it's not something I expect, and the curriculum doesn't expect for you to do. And what you have is, notice I've got 2 points below the line and 2 points above the line. What tells me it's not great data is the first two are below and the last two are above. The second two are below, the last ones are above. Better would be if they're kind of scattered a little bit, one on top, the next one on bottom, top, bottom, so that they're all very close. But that being said, we could deal with this. Now, we talked last day, if I asked you then to take the slope of this graph, is going to be rise over run. So you'd pick points where the line that you drew goes through or very close to some of the little cross marks on your graph paper. Now, if I was doing this, one of the things you never want to do is choose the actual data points from your data. So you're going to want to actually choose points on the graph if I'm asking you to find the slope. So I look here and I say, well, right here, that looks like a pretty good intersection point. Okay, so something like this. Here we've got an intersection point. And I saw another one. This one here is pretty good as well. Okay, so if we're taking the slope of this graph now, I'd like you to pause it, see what you can come up with. Remember, slope is rise over run, so we're looking for how high is it from here up to here. So that distance there, that's our rise, that's the distance it traveled. And then the run is going to be from here, so the time from this time here, 1.5 seconds, up to 6.5 seconds. So pause this, see what you can do. Really pause it, don't just watch me do it. Alright, so my y2, that's going to be this point, my second point, and y2 is going to be 4.5, and y1 will be 1, so 4.5 meters minus 1.0 meters, all divided by my run. And x2 is this point here, is going to be 6.5 seconds minus 1.5 seconds. And our slope then is going to be equal to 3.5 meters per 5.0 seconds, which means our slope, punch that into our calculator, divided by 5.0, and we are left with 0.7, keep the units, 0.7 meters per second. And so the average speed of this object graphically would be 0.7, I guess actually 0.70 meters per second. Okay, and that would be what we do with the slope of this. Now, a couple notes about the graphs. You'll have more chance to practice this in a bit. Couple notes just about graphs and what we can do with a graph and what they tell us. Okay, distance versus time. If we have a distance versus time graph, like this one. Now this is not a flat line, this is a straight line, but it's not flat. If we have a straight line, sorry, we'll get to straight line in a minute. If we have a flat line, it means the object is at rest, not moving. Please fill these in. Pause as you need to. If the line is moving upwards or positive slope, the object is moving forwards. If the line is moving downwards, so negative slope, the object is moving backwards. The slope of the graph, if we find the slope of this graph, it tells us the velocity or the speed. Depends on if we're given direction or not. If the line is straight, so like this one here, we were able to draw sort of a straight line. A straight line means uniform or constant velocity. If the line is curved, this means we have a changing velocity or accelerated, accelerated motion. Okay. In Science 10, Physics 20, Physics 30, curved lines don't tell us a ton. If you decide to take university and you learn calculus and all kinds of fun math, curved lines tell you more. For us, curved lines aren't going to help us a bunch. So if we see a curved line, we say, great, it's accelerated motion, or we'll look down here at what that means with velocity versus time. We can say a few very general things, but what we don't see or can't do with it is any calculations. Okay? With a straight line, we can do stuff with it. We can find the slope, which tells us velocity or speed. Coming back to the slope, rise over run for distance versus time is going to be distance over time. Hey, distance divided by time, that's equal to speed or velocity, again, depending on if we're given direction data or not. All right. What about a velocity versus time or a speed versus time graph? Well, a few things we can learn from these ones. First of all, a flat line at 0 means the object is at rest. Flat line other than 0, the object is in constant motion. Okay, so if you have a flat line at positive 3, it's moving at positive 3, whatever the velocity units are. If you have a flat line at negative 3, it's negative 3, so it's moving backwards at whatever the velocity units are. Okay, if the line is moving upwards, we have a positive slope, we have accelerated motion. It's speeding up. If the line is moving downwards, we refer to this as accelerated motion, but in this case we would say in English that it's slowing down. And the slope of this graph means, or tells us, the acceleration. Okay, so if you look at, again, velocity versus time, we're going to have velocity divided by time. Hey, again, looking back at our math or at our formula sheet, acceleration is equal to the change in velocity over the change in time. Cool thing with this, for teachers, and students don't always appreciate it as much, if you have a velocity versus time graph, you can calculate the area underneath it. And the area underneath it means the distance the object has traveled. Okay? And here you have to look a little bit at the units. So the area underneath whatever the shape happens to be is going to be velocity multiplied by time. Now let's look at the units. What if we have meters per second times seconds? Seconds are on top, seconds are on bottom. We're left with meters. Okay, and so we get the distance. Okay, again, if we have a straight line, whether it's flat or otherwise, we have uniform acceleration. It's speeding up at a constant rate or slowing down at a constant rate. Okay. If the line, however, is curved, here we're having non-uniform acceleration, and we cannot in Science 10, Physics 20, Physics 30 deal with that other than we can say, oh, it's slowing down, or oh, it's speeding up. Okay. When you're finished this, there will be an assignment for you to do. Thank you.